Euclid's division algorithm. To obtain the HCF of two positive integers, say c and d, with c greater than d, follow the steps below. Step 1. Apply Euclid's division lemma to c and d. So, we find whole numbers, q, and r such that c equals d into q plus r, 0 less than or equals to r, less than d. Step 2. If r equals 0, d is the HCF of c, and d if r is not equal to 0, apply the division lemma to d and r. Step 3. Continue the process till the remainder is 0. The divisor at this stage will be the required HCF. This algorithm works because HCF c, d equals HCF d, r, where HCF c, d denotes the HCF of c and d, etc. Let's now look at some more examples on Euclid's division algorithm. Example 1. Use Euclid's division algorithm to find the HCF of 135 and 225. Solution. By applying Euclid's division algorithm, we have: Step 1. Since 225 is greater than 135, we apply the division lemma to 225 and 135 to get 225 equals 135 into 1 plus 90. Step 2. Since the remainder 90 which is not equal to 0, we apply the division lemma to 135 and 90 to get 135 equals 90 into 1 plus 45. As remainder is not equal to 0, division is continued. Step 3. Now, we consider the new divisor 90, and the new remainder 45, and apply the division lemma to get 90 equals 45 into 2 plus 0. The remainder has now become 0, so our procedure stops. Since the divisor at this stage is 45, the HCF of 135 and 225 is 45. Notice that 45 equals HCF 90, 45 equals HCF 135, 90 equals HCF 225, 135. Therefore, using Euclid's division algorithm, the HCF of 135 and 225 is 45. Example 2. Use Euclid's division algorithm to find the HCF of 196 and 38,220. Solution. Since 38,220 is greater than 196, we apply the division lemma to 38,220 and 196 to get. By Euclid's lemma, A equals BQ plus R, here 0 is less than or equal to R less than B. 38,220 equal to 196 into 195 plus 0. The remainder becomes 0, so our procedure stops. Since the divisor at this stage is 196, so the HCF of 38,220 and 196 is 196. Therefore, using Euclid's division algorithm, the HCF of 196 and 38,220 is 196. Example 3. Show that any positive odd integer is of the form 6q plus 1, or 6q plus 3, or 6q plus 5, where q is some integer. Solution. Assume A is a positive odd integer. We apply the Euclid's division algorithm with R and B equals 6. Since 0 is less than or equal to R less than 6, the possible remainders are 0, 1, 2, 3, 4, and 5, that is, A can be 6q, or 6q plus 1, or 6q plus 2, or 6q plus 3, or 6q plus 4, or 6q plus 5, where q is the quotient. As A is odd positive integer, A cannot be 6q, or 6q plus 2, or 6q plus 4, since they are divisible by 2. Therefore, any odd integer is of the form 6q plus 1, or 6q plus 3, or 6q plus 5. Example 4. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Solution. To find the maximum number of columns in which they can march, first, we will find HCF for 616 and 32. Then, this number will give the maximum numbers of columns in which they can march. Now, let us use Euclid's division algorithm to find HCF of 616 and 32. Applying Euclid's algorithm to 616 and 32, we have 616 equals 32 into 19 plus 8. As remainder 0, division is continued. 32 equals 8 into 4 plus 0. As remainder equals 0, division is stopped. So, the HCF of 616 and 32 is 8. Therefore, the maximum numbers of columns in which they can march are 8 columns. Example 5. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Hint. Let x be any positive integer, then it is of the form 3q plus 1 or 3q plus 2. Now, square each of these, and show that they can be rewritten in the form 3m or 3m plus 1. Solution. Let a be any positive integer, and b equals 3, as 3m plus 1 is of the form bq plus r, by Euclid's lemma. We know that a equals bq plus r, where 0 is less than or equal to r, less than b. Then, a equals 3q plus r, for some integer q is greater than or equal to 0, make it as equation 1. Since 0 is less than or equal to r, less than 3, the possible remainders are 0, 1, and 2. Consider the following three cases for r equals 0, r equals 1, and r equals 2.